Hey everyone, my name is Sunay and this is discussion 8, question 3.
Okay, performance analysis. So before you start, I think it's a good idea to understand why we even do these kinds of questions where we're figuring out delays and cycle lengths. And so all of this is really important in figuring out how fast our clock can actually tick and therefore how many instructions we can run in a given amount of time. And so this really dictates how fast our CPU and really our computer can run. So it's a pretty important topic. And with that being said, let's jump into 3.1. So with the delays provided above for each of the data path components, what would be the fastest possible clock time for a single cycle data path? So to help answer this question, let's take out the data path. So this is the drawing that we typically use. And we're essentially just going to be running through, starting from the PC, right? This is where our data path kind of starts from. Is it outputs a value on the from the PC, the program counter, which is an instruction address, and then it goes through and performs that instruction. And so let's just step through each part and figure out how long it takes any generic instruction to run. So we start off with the PC, and the first thing that we have to add is the clock to key delay out of the PC, right? How long it takes for that register to output a value. So this is the time for the clock to key delay. Okay. Next we have our instruction memory. And so we use our address from the PC to actually read an instruction out of instruction memory. And so this is just a memory read operation. Okay. And then next, we need the time for the register file read, right? We split our instruction and read each of these registers. Actually in parallel with this is the immediate generator. But we'll see that the register file read takes 150 picoseconds, and the immediate generator is, well, it's not even listed, it's kind of negligible. But it's really just one big mux, and so it takes 25 picoseconds, so a lot less time. These actually happen simultaneously, so we can kind of ignore the immediate generator for now. And so we'll only consider the register file read here. Okay. Now out of the register file, we see that we have a couple muxes, and then we also have a branch comparator. And so again, if we think about it, for branch instructions, these are the only things that are really going to be using the branch comparator. This happens simultaneously with the mux and the ALU. And so we can actually calculate, so we see that the branch comparator takes 75 picoseconds, and the ALU itself already takes 200 picoseconds. So again, we can kind of ignore this branch comparator down here because it's happening at the same time as these two guys. And so we only need to concern ourselves with this path. And so we see that we need to add in the time for a mux and the time for the ALU. Okay. Next, we have our data memory. So the ALU outputs, and for load words or store words, it could output an address, which we use to read from memory. And remember that since we're trying to find the fastest possible clock time, that's dependent on the slowest cycle that we can have. And so our slowest cycle will actually be on memory operations, where we're using kind of all these components of the data path. And so our memory operation is going to use this data memory, so we do need to include the time for a memory read from it in our calculations. Okay. And then right next, after the data memory, we have this write back select mux, where we're choosing between the ALU output, PC plus 4, and our output from memory. So we have the time for a mux. And then finally, we write back whichever value we chose all the way back to the register file into our destination register. And so this would happen for load words. And so we need to take into account the time, the setup time for this register file, since it is also on a clock, right? So this is basically just an array of a bunch of registers. And so we need, in order to write to any given register, we need to take into account its setup time so that we write properly. Okay. And that should be all the components that we need. So let's add all these together. Our clock to queue time is 30 picoseconds. Our memory read operation, 250. Our register file read is 150. The time for a mux is 25. The time for the ALU is 200. By the way, this is for the PC. I forgot to make a note of that. And this is for the register file. I'll just put RF. Okay, so this was the ALU. Now the time for another memory read is another 250 picoseconds. Then the time for a mux, 25. And the time for a register file setup, which is 20. And we notice that it's the same in this case as register setup. And this is pretty common because since this is just a bunch of registers, we really only care about the setup time for any one register. Okay, and this all sums to, I believe, 950 picoseconds. Okay, and remember it asks for the fastest possible clock time for the single cycle data path. This gives me the slowest possible cycle, and so to find the fastest possible clock time, I just need to do 1 over this. So 1 over 950 picoseconds is going to be 1.05 gigahertz. Okay. And so this is the fastest possible rate that our clock can run at. And this is for the single cycle data path. Okay, so now in 3.2, let's analyze the fastest possible clock time for a pipeline data path. So let's bring in our pipeline data path here. Now here, we have our registers laid out already. And so in order to do this question, remember that the fastest possible clock time for a pipeline data path depends on the slowest stage of the data path. So by stage, I mean the time, the piece, the segment in between any two registers. And so once I find the slowest possible stage, that will give me the fastest possible clock time, because I obviously can't go faster than that, or that one stage won't run properly. Okay, so let's, in order to do this question, let's actually just take a look at every single stage individually and calculate how long it takes. And then we'll see which one takes the longest, and our clock time will be dependent on that. Okay, so first up is the instruction fetch stage, which is this first part here. So instruction fetch. Now the instruction fetch stage really starts at the PC register, again just like in the single cycle data path, and you'll see that this part before the register, this mux, is actually kind of part of the execute stage, right? Because we're writing back a value from our ALU, and we're choosing between that and PC+4 in this mux, and so that piece is actually part of the execute stage and not the instruction fetch stage. So remember that each stage starts with a register and ends at a register. And so here the instruction fetch starts at the PC register, which again is just a register like any of these, except that it holds a program counter. And it ends at these instruction decode registers, okay, which are used for pipelining. So the time for the instruction fetch stage is really just going to be a clock to queue delay of the PC register. So time for a clock to queue, plus the time to read from instruction memory. So we have a memory read operation. And then we add in a setup time for the next set of registers. And we'll pretty much see this in every stage. We start off with the clock to queue. That's the time it takes for the previous register to output. And then we end with a setup time, which is the time it takes for the next set of registers or the time that we need to have the value right before the next set of registers ready so that it can be read properly. Okay, and if we calculate this, add all of them together, we see clock to queue is 30, memory read is 250, and setup time is 20. And so this takes a total of 300. So maybe I'll write this. This is 30 plus 250 plus 20, which is 300 picoseconds in total. Okay. Now let's look at the instruction decode stage, which is our next stage. And so this one again starts with a register, and so we need to include its clock to queue time. And then we add to it the time it takes to read from the register file. Okay. And once again, just like we saw with the previous part, this happens simultaneously with the immediate generator, so we don't need to worry about counting this. And then finally, after the register file, we see that we have another setup time for the next set of registers in the pipeline. Okay, so we add the time for a setup, and this is 30 plus the time for the register file, which is 150, plus the time for setup, and that'll adds to 200 picoseconds. All right, I've run out of room, so I'm just gonna write here. So next in our execute stage, we start off with these registers again, so we again need to have a clock to queue time. And once again, as we saw with the previous part, this branch comparator happens in simultaneously with these muxes and this ALU, and so we can kind of ignore that and just count the time for the mux here. And remember this A select and B select muxes, these also happen simultaneously. And so that's why I'm only counting one mux and not both of them. Okay, and then I add the time for the ALU. And here's where things get a little tricky. So I see that I have kind of two branches coming out of this ALU. One of them goes into this next set of registers here, and so I would need to add the setup time for this. The other one actually goes into this mux, and then to the PC register. And so I'd also need to add the setup time for this. And since this time takes a little bit longer than the setup time here, I'll add that leg. All right, this is the longer of the two legs. So this is the time for this mux out here, the PC select mux. So let me make a note of that. This is PC select. All right, the control signal that's fed into it. And then we have this setup time for the PC register. Okay. And if we add all of these together, my clock to queue delay is 30. The time for a mux is 25. Time for the ALU is 200. The time for another mux, another 25. And then the time for setup is 20. And this all adds to 250, 300 picoseconds. Okay. All right, next stage. Let's do the memory stage now. So here, once again, we start with a clock to queue time out of these registers. Then we have a memory read operation. And so, or a memory write. But we see that the memory read actually takes longer than a memory write in this case. And so we use that. Okay. Next I have a mux, which is my write back select mux. So the time for a mux. And finally I have another register. So I need to put in the setup time for that. Okay, and in general, by the way, while I was doing this question, I was always considering the longest path. So yes, there's a path that is just a direct wire that skips the memory operation and goes directly to this mux. But I actually want to be including the longest path in my calculations, because that's going to tell me how slow or how fast I can make my clock, right? I can't make my clock faster than the longest path takes to run, because that will result in timing issues. Okay, so this equals 30 plus time for a memory read is 250, plus time for a mux is 25, and then a setup time of 20. And it looks like we have a new winner here. So this is 325 picoseconds. Okay, and then finally, I'll write the write back stage down here. Or I'll write it on the side here. All right, write back. So here I'm starting with this register. It takes clock to Q seconds or picoseconds to output. Then I add to that this is just one wire, so I don't have any delays here. And then I add to that the setup time of the register file. So this is the register file. And then I'm done, right? That's my write back. So this is just 30 for the clock to Q and 20 for the setup, which is 50 picoseconds. Okay. All right, so now I've calculated the longest cycles in each of these stages, or the longest paths in each of these stages. So now I can find the longest one out of all of those. And 300, 200, 300, I see that the longest one is 325 here, which is for my memory read stage, or sorry, my memory stage. And so that dictates the fastest possible clock time that I can have. And so the fastest time is, so 325 is the slowest cycle, so 1 over 325 is the fastest time, which is, let's see, looks like about 3.1 gigahertz. Okay, so significantly faster than this. All right, 3.3, what is the speed up from the single cycle data path to the pipeline data path? And why is the speed up less than 5? So to find the speed up, I'll just take the time for the single cycle and divide that by the time for the pipeline version. So that's 950 divided by 325, which is about 2.92. So I get about a 2.9 times speed up. Okay. Now, why is this less than 5? So if you remember, when we're adding all these registers, instead of just having a wire, for example, from my instruction memory to the register file, I actually had a register in between. And so along with that register comes a setup time and a clock to Q time. And I have to add that for every single stage. Okay, so that's part of it. That actually slows down my clock a little bit. And the other part is that instead of just basing my clock time off the exact timing it takes for each of these pieces of the data path, I'm basing it off the slowest stage. And so even if I have one stage that goes faster, so it can go faster than the clock time that I've set, I'm still basing that stage off the slower, the slower clock, right? The longer clock cycle. And so those are kind of the two components for why this speed up is less than 5 times. Okay, so that's question 3.